Okay.
Okay, so it's a great pleasure to welcome Tommy Murphy of Cal State Fullerton. I'm sorry, you want to share your screen first? I didn't realize that. Who will speak on Riemannian three symmetric spaces, the moduli spaces, and Ricci solitons.
Okay. Hi, everybody. And thanks very much for coming on. Can you all see my screen okay?
Um, oh,
I see it on.
are others seeing it? I was seeing it before, but now I'm not. Am I the only one not seeing it? Oh my
Can't see this.
goodness.
Yeah,
It was.
it's there. It's the iPad, right?
It's the iPad, yeah.
Yeah.
So I'm signed in on my computer and I have an iPad for in case I want to write. So the iPad is the.
Huh.
I can just do one device if that's better.
Well, if everyone else is seeing it but me, I think
Will it
I'll
want to
sign
affect?
up and join
Oh,
back in and
Carolyn,
you can go ahead and start.
Will it
I
affect the?
let me say this is new for me. At the top of my Zoom, I see tabs, and one is the meeting with pictures of everyone, and a
Yeah.
different tab is Tommy's presentation.
Oh, no, oh, thank you.
Okay. So we're good.
I'm good. So sorry for that.
Okay, good. Hopefully that works out well for the recording. Okay, hello everyone. Thank you so much, and thanks for the invitation to speak here. Um, I've followed this seminar for a lot of years, especially with a young family. It's been great to be able to stay connected online, and I'm glad to give a talk today about a paper. So I want to talk about three symmetric spaces, which is kind of a classical topic, and a chunk of the start of the talk will involve some technical delving into definitions. So firstly, I wanted to maybe set the scene a little and put the problem in context and explain a bit why you should care. So this is sort of propaganda or something. So for example, a kind of a foundational question in Riemannian geometry is to do with how one generalizes uniformization. And there's sort of there's two perspectives you could take on this. The usual one is to say the best metric generalized to higher dimensions would correspond to Einstein manifolds. But the approach I want to take today is actually to say, well, actually, I'm more interested in viewing the best metrics as Riemannian homogeneous spaces. Namely, there's a transitive group action, and the metric is invariant under that group action. So, for example, if we were to generalize to higher dimensions, you see, if you generalize constant scalar curvature, you get Einstein manifolds. And obviously, there's been, a lot of focus and a lot of talks in the seminar around this topic. But if we wanted to generalize homogeneous spaces, maybe the higher dimensional generalization would be symmetric spaces. And say classically, for instance, it's probably, or in research, it's probably fair to say that more focus falls onto studying questions on Einstein manifolds, because, for example, the symmetric spaces are classified, and then you could ask, well, how do you generalize it? That's what this talk is about. But somehow you might think, well, that's just a kind of a finite problem. We're just going to be classifying lists of Lie groups or something. Why is that interesting, right? So one aspect of this is, for example, one reason Einstein manifolds have attracted a lot of attention is because they can admit rich moduli spaces, which generalizes, say, Teichmuller space. And one of the surprising things today is we will see for three symmetric spaces, such phenomena also happens. And that's something that I think is really notable. So, for example, a couple of years ago, and this is just blatant advertising, I discussed, the problem of showing if SU2n plus 1 is rigid or isolated. And 'cause this is an interesting problem because there's an infinitesimal description of the moduli space. And then the question is, can you actually genuinely integrate some of these infinitesimal deformations to get a genuine moduli or curve of Einstein metrics? You can't, and there's been many talks in the seminar on this topic in recent years. Okay, so what I'm trying to say is, classically, a lot of interest has focused on studying Einstein manifolds, because of this moduli space structure. But I want to draw attention to this natural generalization of symmetric spaces because there's also some very notable and rich behavior happening there. Another reason you might care. Okay, so here's a theorem that I will explain how the proof works later, but it's a fully general construction of Ricci solitons. So if we take a simple Lie algebra and any faithful representation, then this manifold, so it's a semi-direct product of V and the Lie group associated with my Lie algebra, and then you mod out by the K is the Lie group associated with this Lie algebra. This will admit a Ricci soliton metric. So this gives you a fully general construction of expanding Ricci solitons. Just to explain some notation here, semi-direct products will be very important in our talk. L is our Lie algebra. I prefer to state things at Lie algebra level. So this is the corresponding group. And this representation pi, if you differentiate it, you get this representation rho. And to explain what a semi-direct product is, you will see this naturally occurring later in the talk. It's basically you take the direct sum of the vector spaces V and L, and how do we give it? So L is a Lie algebra, so we can give it a natural Lie bracket. The vector space V is flat, so that's the Lie bracket of two items in V, and then the cross terms, well, the natural thing to do is to feed rho and L into the representation, and then feed in V. And so this is how we define a Lie bracket on this structure to give it a Lie algebra. Okay, so let's start with some classical definitions. Okay, so we kind of go back to school. So a K-symmetric space is a manifold which admits a family of isometries. So for every point, there's an isometry of order K. And there's also this regularity condition, which you don't need for the classical symmetric spaces, but authors included for the higher dimensional ones. So I'll just throw it in as well. There are better definitions than this, but this is where the word symmetric comes from because this is the symmetry that is around each point. Okay, so for instance, of course, you probably can guess what I'm going to say. When K is 2, we get our classical Riemannian symmetric spaces due to Elie Cartan. And here the assumption of regularity isn't needed. Probably it's better to think of these. They have this beautiful geometric description that the curvature tensor is parallel. So this is locally maybe a better way to think about it. But the words I wanted to explain firstly where the word symmetric came from. Okay, so some general theory, which we'll need to discuss is, if you look at how these objects are actually classified, there's various things you can do. So for example, if you just start off with all these symmetries, how do you write down the group? So this is called the transvection group. And it's given by the groups of all symmetries, which are how we define symmetric spaces. And if you take this group, then you can realize your manifold as a Riemannian homogeneous space, G mod H, where here H is the identity component of the fixed point set of. So this is an isometry that squares to the identity set. Okay, so this is how you classically can realize this as a symmetric space. Then, of course, what one does is this allows you to reduce to an algebraic classification. So this allows you to split your Lie algebra G as H plus its complement, and then you classify symmetric pairs. And then one thing to say, which is going to be important, is that then the story is not over. So you start with a Riemannian manifold, you turn this into an algebraic problem, you classify the symmetric pairs, but then you need to go back to the manifold level. And this is not an issue for this classical symmetric spaces, but in general it is. And that's going to be important for us later on. Okay. So today we want to study three symmetric spaces, which is where we just replace 2 with 3. So if you like, we have an automorphism of the Lie group that cubes to the identity, and we're constructing the corresponding homogeneous space. It's not immediately obvious that this is very interesting. It might just be some sort of like naive, silly generalization. Okay. So if we have working at Lie algebra level, if we have an automorphism that cubes to the identity, then we can split our Lie algebra. This is just simply like factoring the polynomial x cubed minus 1. It's going to factor as x minus 1 times x squared plus x plus 1. So our Lie algebra will split in this way. Okay, and one reason that these are important to study is they play a very prominent role in various flavors of almost Hermitian geometry. So for example, they admit a natural complex structure. So every talk should have a calculation, an easy calculation to start. So firstly, let me show you why this is an almost complex structure. So we're going to square this operator. So if we square this operator, we're just going to square this, right? And this is restricted to the tangent space V. So that's going to give us 1/3 the identity plus, and then we have twice the cross product, 4/3 sigma, and then we square 2/√3, and we again get 4/√3 sigma squared. Okay. But we're restricting to the space V, and on V, sigma plus sigma squared is equal to -1. So this is all equal to -1. And so you get, oops, typo, there, that should be 4/3. And so you get 1/3 times the identity plus 4/3 times minus the identity. And 1/3 minus 4/3 is -1. So you get a genuine almost complex structure. Okay. So it turns out actually not just is this an almost complex structure, but it's quasi-Kähler, which is it says the associated symplectic form is holomorphic. So it's a natural class in these Gray-Hervella classification. All right. Okay. Another reason you might care about them is they occur naturally in the study of nearly Kähler manifolds. For closed homogeneous manifolds, being three symmetric is the same as being nearly Kähler. What's nearly Kähler? I know there's a lot of definitions, but nearly Kähler is quite a simple definition. Kähler says that J is parallel. So this is how you can write down a parallel if you feed into vector fields X and Y. And nearly Kähler is simply you let X equal to Y, you sort of take the trace, and you get, this is the simplest way to write this condition. Okay. Why are nearly Kähler manifolds important? They occur in many famous, sort of at the intersection of a lot of interesting topics. So for example, the famous almost complex structure in S6 is nearly Kähler. In G2 geometry, if you take the cone over a nearly Kähler 6 manifold, you can get G2 metrics, and they occur a lot in string theory, for instance. So they're an important topic, and three symmetric spaces are closely related. Okay, we will need the structure as well in a little. Okay, so let's give some examples, some simple, well-known examples. So the first family of examples are every Hermitian symmetric space can be viewed as a three symmetric space. Okay, so how does this work? Well, you have your usual Cartan splitting. G is H plus V. And we're going to define our automorphism to just be 1 on H. And here we're going to take a cubed root of unity, Z0 plus Z1. And obviously when you cube this and use the J squared is -1, J is the complex structure, making this a Hermitian symmetric space, then it'll just, you can just check that it satisfies the sigma squared plus sigma plus 1 equals 0. Okay, so it's a nice family of examples. Now, let's give a more interesting example to show you why this is like a rich problem. So there's a famous construction of this twistor space of quaternionic projective space. And actually, this is how we got interested in this is, I should say everything I'm talking about is joint work with Paul-Andy Noj. And a few years ago, we wrote some papers coming from Riemannian geometry, studying complex Riemannian foliations. And this is really how we got interested in the problem. Okay, so let's explain how this happens. So firstly, we have our famous Hopf action. So if we take this 4n plus 3-dimensional sphere, you can add there's an isometric action by a circle, and the quotient space is CP2n plus 1. Okay, but this is a special dimension, of course, because it lives in quaternionic space. So you can also act by S3. And if you act by S3, this is the generalized Hopf action. This is how you can construct quaternionic projective space. Okay, so these are both Riemannian symmetric spaces. For example, how do you give them the metrics? So you give this the round metric, this acts by isometries, and this is how you can construct the Fubini study metric. Similarly, you give this the round metric, this acts by isometries, and this is how you construct the usual symmetric space metric on this space. Okay, so you have a Riemannian submersion going from here to here, and you have a Riemannian submersion going from here to here, and you can ask, what's the difference? Well, when I go from a point here down here, to the fiber here is an S1, but the fiber going down from this map is an S3. So the difference between them is S3 mod S1, which is S2 by the classical Hopf map, or CP1. And so in this way, you actually get a Riemannian submersion from this space to the base, and each fiber is a CP1. And so this is a complex Riemannian foliation. So this is where the story starts to get interesting. CP2n plus 1 is a Hermitian symmetric space. So by our first example, it's a three-symmetric space. Okay. At the same time, I just showed you that this is a Riemannian submersion with complex leaves. And there's a standard, this is called the canonical construction in Besch. It's like chapter 9 or something. And there's a natural way to build an almost complex structure. It turns out to be nearly Kähler on it. And that's given by you multiply the metric by a half in the vertical direction. You leave it alone in the horizontal direction. And this is what you do with the almost complex structure. And this gives you an almost complex structure. So if you're interested in this, I'm sure most of you have read this, but it's chapter 9, Besch has this construction. And so this is a standard construction, and it turns out that actually this is nearly Kähler, and you can directly check that by the simple identity equation I wrote down earlier. So what's the upshot? The upshot is we start to see behavior happening that doesn't happen in general, right? Or doesn't happen in the classical theory of symmetric spaces. We have, on the same Riemannian manifold, we have two different three-symmetric metrics. One is the Hermitian symmetric space, and one is this one coming from the Eel-Sampson construction. So there's two different metrics. In fact, there's three, because you can, so the isometry group of the nearly Kähler metric is SPN, and the SPN is the transitive group, which is how you can describe this as the three symmetric structure, but it's not the full isometry group. The full isometry group is SU2n minus 1. And so there's a larger group, or there's a strict subgroup of the isometry group acting transitively. And so you can, this actually turns out to give you three different three-symmetric metrics, because you can twist the almost complex structure by the full isometry group, and that doesn't preserve the original nearly Kähler structure. So it turns out that we have three different three-symmetric metrics living on the same manifold. And just to observe, this is sort of stuff never happens in our classical. In Cartan's classical theory, you do this Lie algebra classification and then you go back. Okay. Now it could turn out that some of these, when you build these homogeneous spaces, they could turn out to actually be the same. There's different presentations of, say, a sphere as a homogeneous space. And that just doesn't happen. But here we start to see this happen. And one of the reasons that classifying these objects has been kind of hard is because, like, what we're seeing here is that the group, the metric, they're all sort of bound up together, the almost complex structure and the definition. And so it's not easy to separate them. And so that was really kind of the phenomena we were seeking to understand. Okay, so here's another definition. This was also, I think, was known to experts. So in general, when you have a almost Hermitian structure, there's a canonical Hermitian connection you can build. And three symmetric spaces this is just unwinding definitions. You can think of them as being just satisfying this quasi-Kähler condition, but this canonical connection is an Ambrose-Singer connection. Okay, so these give you a very beautiful algebraic model, and you can use this algebraic model to study the homogeneous geometry. It's, of course, generalizing the classical, so for symmetric spaces, if you take the Levi-Civita connection, the torsion is 0, so it's parallel, and the curvature is 0 is our local characterization of symmetric spaces. So this is a nice way of generalizing it. Okay, and that's why these objects were first introduced by Ambrose and Singer. So this allows us to sort of algebraically classify or study these objects, right? This gives us sort of an algebraic model. Okay, so we have a Chern connection. The Chern connection or canonical Hermitian connection is Ambrose-Singer. So for example, now I can rigorously prove that Hermitian symmetric spaces are three-symmetric. earlier on, I just wrote down a map and I said, oh, this works, but how would you prove this? Well, if you have a Hermitian symmetric space, scalar implies quasi-scalar, so it's scalar. And if you just take the Levi-Civita connection, as I just said, the torsion is 0, so this is 0, and by definition of being a symmetric space, this is 0, so we get that it's 3-symmetric. So this is how you can prove, for example, the simplest examples are 3-symmetric. Is that okay so far? Okay, cool. But again, we see here the same issue, okay, which is that the metric, the almost complex structure, and the group action are somehow bound up together. This was really how we started out thinking about the problem. But now there's a new issue. So of course, this is a very nice generalization of the study of symmetric spaces. It gives you a powerful algebraic tool. And so what's the problem? What's the drawback? The main drawback is you have to worry about what's called regularity of your infinitesimal model. And what regularity is talking about is if you have this infinitesimal algebraic model, can you actually realize this? Can you build a manifold? Okay, so you start with a manifold, there's an associated algebraic model. Now we're studying the algebraic models, but how do you know you can go back and realize the manifold? And this is a subtle issue. So for example, there's a very nice work of Tricheri and Van Heck, where they construct like infinitesimal models that you can't integrate, so that do not correspond to a homogeneous space. And so this is one of the technical issues we're going to have to talk about. Okay. So finally, we come to our final definition. So just playing with the definitions, you can actually break this up to say it's an Ambrose-Singer connection D, such that the almost complex structure is parallel and the torsion satisfies this, anti-commutes with the almost complex structure J. So this is just a direct computation. But as you'll see here, there's no mention of a metric. Okay, so this is one of the ways we're going to be able to make progress. We're going to take this as a definition of 3-symmetric. And to get back to our classical definition, we are going to say it's Riemannian 3-symmetric if the holonomy group associated with this connection is compact. Okay, so how did we come up with this? Well, firstly, the holonomy by the Ambrose-Singer theorem, the holonomy Lie algebra, I mean, this is really the key thing to take away. That's the isotropy of your infinitesimal model. Okay, and if that's compact, then it's standard that your infinitesimal model can be integrated up to give you a manifold. Okay, so that's really why we were led to make this definition. Equivalently, I mean, this is sort of a standard fact. This is equivalent to saying that you can find that compatible metrics are the same thing as this is a standard argument as having metrics G which are parallel. So for example, if G is parallel and J is parallel, then the holonomy group is going to be, or the holonomy group is going to be a subgroup of SOV G, and that's any subgroup of a compact Lie group is compact, so you get that this is compact. And going the other way, if this is compact, you can apply an averaging argument, just like when you construct the Haar measure, you can construct an averaging argument to get a parallel connection. So this is another reason that it was a natural definition to be led. Okay, so right now we have this sort of, I guess it seems like I've gone down the rabbit hole of getting into these quite technical definition, but we really needed this because we needed to be somehow able to decouple the metric and the sort of algebraic aspects of the problem. Okay, so let's start stating some theorems. So for example, this is always true that you start with a 3-symmetric space as we've defined it. You have this transaction group. It always acts transitively, okay, at Lie algebra level. So what's happening here now is that we have G is equal to H plus, and the complement will be given by V. And actually, you can build your transaction Lie algebra G by this formula. It's given by V plus the Lie bracket of elements of V which itself. Okay. So the first theorem is as follows. Every 3-symmetric space can be written as a Riemannian product given by the following factors. So we have 3-symmetric spaces where the transitive group action is semisimple, and then these are two-step nilpotent, and then we have these type 3 and type 4 spaces. Okay, so I should say, if you've ever read about three symmetric spaces, there's a famous work of Gray and Wolf, and they studied this case of semisimple. Two-step nilpotent, this corresponds to manifolds with flat Chern connections. And so there's work of Di Scala, Lauret, and Vezzoni on this. But we can't classify these. This is kind of beyond what we can do. But what we do is we completely classify these guys. And really, I mean, today I'll just focus on the type 3 spaces, but these are very interesting. So really the main point of the paper is to understand these. Okay. Okay. Let me maybe say a little bit about how this proof works. So basically we have this canonical Hermitian connection, and by kind of how we've defined everything, this turns out to be an Ambrose-Singer connection. So as I said, the fact that we have defined our holonomy group to be compact, that's what makes our infinitesimal model to be regular, and that's how we can get a classification at manifold level, how we can go back from this algebraic description to this manifold. But the other key thing is as follows, really. I mean, the main punchline is as follows. There's this Levi-Malchev theorem, which is sort of the foundational theorem when you study like Lie algebra. We're stepping outside this sort of standard semi-simple world, and your main tool when you first study Lie algebra or the first main result is this Levi-Malchev theorem. So it gives you a decomposition. Okay, so any real, say, Lie algebra can be written as a semi-direct product. Here we see the semi-direct products emerging that you saw stated in the Ricci soliton theorem. And it's the semi-direct product of, so this is the Levy factor, it's semi-simple, and in general, semi-simples are easy to understand, or semi-simples we understand. And any Lie algebra can be written as a semi-direct product of the semi-simple factor with what's called the radical, which is the maximal solvable ideal. And why, in a nutshell, why Lie algebras are so hard is that it's very hard to understand the solvable Lie algebras, and so we have no idea what to do here. Okay, but this three symmetric space condition actually tells us something much. Oh yeah, this tells us something very important. We actually managed to get this geometric description of the radical, and that's really why we can prove things. So the punchline is that under this three symmetric condition, we can actually geometrically describe the radical, and that's what allows us to get classification results beyond the semi-simple case. Okay. Okay. So this is basically how the proof works. Then we have to like break it apart into the various parts. So now I want to, oh yeah, so this is a summary of what I want to say. Yeah. So semi-simple were now classified here. We have to be careful. A lot of people, when I talk to them about this problem, are adamant that this was classified by Gray-Wolf. There is an extra assumption. So if you actually look at their paper, they're assuming that all the isometries are holomorphic, that they also preserve the almost complex structure J. Okay, so we can also make some progress on this, but that's not necessarily the case if you take the classical definition of a three symmetric space. So I'll come back to that later. Okay, so yeah, two-step nilpotent corresponds to three symmetric spaces with flat Chern connections, and what we really want to talk about are type 3. Type 4 are at Riemannian level products of semi-simples and flat spaces, but they have a sort of twisted, almost complex structure. And these are actually in bijection in a way that comes from this like Lie algebra duality. Okay, so what's a type 3 space? So a type 3 space, I'm going to describe at Lie algebra, right? It's enough to give me, so this is going to be a homogeneous space. So it's going to be something of the form G mod K, okay? So I'm firstly just going to describe the Lie algebra corresponding to the transitive group action, okay? So what this is we have to take a non-compact Hermitian symmetric space. We take the corresponding Cartan decomposition. So this breaks up into K plus, so the isotropy plus its complement. And then we have to take a special type of representation called an admissible representation, which I'll define now. So once we have this representation, then we take this semi-direct product and then you mod this out by K, and that's the space of type 3. Okay, so this exactly corresponds, to the Ricci soliton example I gave at the start. Okay, so what we need to do now is define what are admissible representations. Okay, and once we have them, then this is how we build a space of type 3. Okay. So again, like how are we led to this sort of complicated definition? Well, it really came from the fact we were able to like geometrically control the radical, and then we were able to, so this is our simple Lie algebra, say. I mean, everything breaks up into products, so this is semi-simple, but this say is a simple Lie algebra, and so you're looking at a semi-direct product, like how this acts on this vector space. You need a representation, and so this is natural. So we just unwound the definition, and we were led to this. Okay. So what's admissible? So a representation is said to be admissible if the isotropy commutes with the almost complex. So remembering here we have a Hermitian symmetric space. That means we have an almost complex structure. So it's going to be admissible if the isotropy commutes with J and its complement anti-commutes with J. So this is kind of what came out from unwinding the definition of three symmetric. Okay. In fact, I just want to sort of do one more proof. In fact, we can prove in general these exist. So to do this, let's firstly describe, okay, so I'm going to define a background. So we take a vector space V, and I'm going to define a background metric HV. So this metric is taken to be a reference metric because this metric will always exist. And we're going to use this as a reference metric to describe all the other metrics. So what we have to do is we have to take rho of K is going to be an SOV, is going to anticommute, and then its complement is going to be symmetric. Okay. So firstly, there's kind of a nice proof. Let's show that these metrics always exist. Okay. Once we have background metrics, then I'll explain exactly how this is related to admissible representations. Okay, so this is a nice proof. So how do we do this? Okay, well, we have a Lie subalgebra rho of L, and it's easy to see that there's a Cartan involution. L splits as the isotropy K plus its complement. Okay, and so the Cartan involution has got a +1 eigenspace and a -1 eigenspace. From being a representation, it follows that the isotropy must map forward to the +1 eigenspace and the complement to the -1 eigenspace. Okay. There's a classical theorem of Mosto that any Cartan involution of SLV you can restrict if you have a Lie subalgebra, any Cartan involution of that subalgebra can be realized by restricting one from the ambient space. So we just apply that classical theorem. And okay, but any Cartan involution is given by, if you take some inner product, that's what we call a background metric, it's basically given by the map F goes to -F transpose. Okay, so you see here we have like, if we take, so let's show how this works. So for example, say we have sigma rho of K. Okay, so that's rho of K. Okay, but the Cartan involution this is minus rho of K transpose. So therefore that tells me that rho of K is skew symmetric, tells me it's an SOV. Similarly, I have an extra minus here. So then this becomes, for the complement, I'm going to get, so if I take X in H, okay, so I'm going to get sigma rho. Okay, so what's sigma rho of X? Well, by definition, that's minus rho of X. Okay, but the Cartan involution is F goes to -F transpose. So the Cartan involution, it's minus the transpose of this. So that's minus rho of X transpose. Then the minuses cancel, and we get rho of X is equal to its transpose. Oh, it's symmetric. Okay, so this is not hard to do. Okay. So once you have a background metric, right? How are we going to classify all type 3 spaces? So admissible representations, I now claim, are in bijective correspondence with this classical object in Riemannian geometry, namely totally geodesic submanifolds of this Hermitian symmetric space. So this is the Hermitian symmetric space SPNR mod you are. Okay. So again, this is a kind of a nice thing to see. So how do we do this? Okay, we have an admissible representation. Okay, so that means that rho of k, by definition, is skew. We've proved the existence of a background metric, and so rho of k lies in SOV, HV. That's what we proved here, right? This is what isotropy invariant means. Okay. Okay, cool. But because what does it mean to be admissible? The definition of admissible is that rho of k lies in GL, it commutes with J. So it lies in both of these guys. And if you intersect the Lie algebras SOV and GLV, you get the unitary Lie algebra. Okay. Similarly, if you look at the complement, so what's the symplectic form here? The symplectic form here is HV, JV is built in a natural way out of our background metric, right? So if you look at the complement, well, what we saw here is that it's symmetric. So if you take an element of the complement, it's symmetric, but because it's admissible, it anti-commutes with J, and so this is the complement. So now if we're doing this at Lie algebra level, this is the like Cartan decomposition of the symmetric space, right? And so we see that the Lie algebra rho of L is going to be, is going to sit inside this homogeneous space because the isotropy goes to the isotropy. In fact, now there's just one last computation. So, okay, now take X, Y, and Z lying in H. So that means we're looking at like the image of H. So how do we write this? Rho of H is rho of X such that X lies in H. Okay, so I'm claiming that that corresponds to a totally geodesic submanifold, which is super classical, right? And how that works is, okay, you take rho of X, rho of Y, rho of Z, and we're going to show it's a Lie triple system. So you take the Lie bracket of rho of X and rho of Y, and then you bracket that with rho of Z. Okay, well, because it's a representation, all the rho pulls out from all these guys. You just keep applying that it's a representation, and you get that rho of the Lie bracket of this guy. Okay, but hang on a second. This is a Hermitian symmetric space. So if you take X and Y in H, the Lie bracket of two things in H lies in K. So this lies in K and this lies in H. This lies in K and this lies in H, and the Lie bracket of something in K and H lies in H. So you're done. So what we have shown is that admissible representations exactly line up with this very classical object, namely totally geodesic submanifolds of a fixed symmetric space. And that's how we're able to get a classification. Okay. In fact, these were classified long ago by Satake. I would say that I found Satake's classification is hard to read, or hard to follow, right? So if you look in our paper, one of the things we did is we kind of actually went through every single example and explicitly wrote down how this is an admissible representation, how it satisfies our definition. But yeah, the point is there is this standard list of totally geodesic submanifolds of this symmetric space, and here you go. These are the guys which arise. And so for each of these, we get an admissible representation, and for each of them, that gives us a three-symmetric space. Are there any questions so far? Is it okay? Okay. Okay. Well, let's maybe move on now to explain a little bit about how these are connected with Ricci solitons. So I need to explicitly tell you what the metric is. Okay, so again, I stated this theorem at the start of the talk. This is our Ricci soliton. So how do I realize the metric? Well, we have at Lie algebra level, the transitive group corresponds to this Lie algebra. And L breaks up as, so V is V, and L breaks up as K plus H. So just at vector space level, it breaks up like this. So now what I'm going to do is I'm going to mod out by the Lie group of K. So the tangent space is going to be this V and this H. By the way, this V and H notation is deliberately chosen because this is how we originally, I think, worked on this, is because this is going to actually correspond to a foliation polar foliation. And this is how we originally got interested in the topic. So these three symmetric metrics all admit natural foliations. This is the vertical space, and this is its complement. Okay. So now let me explicitly tell you what the metric is. The metric is given by, well, on V, we have to put one of these background metrics, and that's why I wanted to take the time to explicitly construct it. And then on the complement here, we just restrict the killing form to H. Okay, so, and then T can be any scalar, positive scalar. So, okay, so that's the metric, and you can directly compute that this is a Ricci soliton. So this gives us a fully general construction. Now, what's the connection between three symmetric spaces? There's no mention of three symmetric spaces here. That's because this is any simple Lie algebra. However, so we proved background metrics exist for any Lie algebra. Okay. However, in the case of Hermitian symmetric spaces, these background this exactly corresponds to the three symmetric metrics in our classification. Basically, how does this proof work? Well, all we need is that it turns out because we have a foliation, we have very nice, there's a very nice way to explicitly compute curvature. Yeah, so there's standard formulas to compute curvature given a foliation, and that's really what we use, and we just plug it in and compute out. It turns out that the vertical space V over foliation is the kernel of the Ricci. And this ties back to earlier when I was saying we had this geometric interpretation of the radical. I mean, it's sort of related to this. So since we have this foliation and the vertical directions, the Ricci vanishes. That means the full Ricci tensor is just some multiple. It's just some multiple of. It turns out to be constant and just in the horizontal directions. And so if you want to write out the Ricci soliton equation, this is going to differ from the full metric G by some component by some multiple of the identity in the vertical directions. And we just have to show that's a derivation, and you've shown it's a Ricci soliton. That's the proof. Okay. So I have 5 minutes. So I just want to sort of talk. I mean, there's a lot we do in this paper, and I've sort of never written such a long paper. So I want to maybe say some further things that we can do. So we explicitly compute the moduli space of all three symmetric metrics. And it turns out that for certain examples of these type 3 spaces, there's infinitely many three symmetric metrics. In fact, if you give me a number, an integer d, I can construct a three symmetric manifold whose space of three symmetric metrics has dimension d, so 100-dimensional family or 1,000-dimensional family, whatever you want. We also discuss and give examples, but this is some project for the future. We didn't fully classify all of the homogeneous presentations. So once you fix each of these metrics, it turns out that there is in general a lot of different transitive group actions. That's very interesting. And that again goes back to this simple example of a twistor space at the start of the talk. And we also prove if the actual metric G is not a locally symmetric metric, and I mean in the sense of Cartan, so this is not Riemannian symmetric, two symmetric, if you will, then every isometry is holomorphic. So this goes back to this classical work of Gray and Wolf. They had a full classification assuming that the isometries are holomorphic, and we can show that that's always the case for semisimple three symmetric spaces unless the metric is symmetric. So it's kind of amusing because the symmetric case, which should be the easiest, is the one that's left to handle. And also, actually, we can give an algorithm to completely compute isometry group for any Ambrose-Singer space, which maybe is of independent interest. So sort of a very nice problem or important problem in homogeneous metrics is if you give me a homogeneous space, a G invariant homogeneous space in a metric, how do you compute the isometry group? Okay. So for time, because I only have a few minutes, I'll just focus on the first problem. Okay, this is the last thing I want to talk about. Okay, so if you take one of these three symmetric spaces of type 3, we spend a chunk of the paper describing the corresponding moduli space. So it turns out that what we have to do is we have to basically parameterize this space. So where that comes from, just to remind you, is that, our Lie algebra G broke up as K plus H plus V. Okay. And then we're constructing the Lie group G bar mod K. So we're going to kill this guy. And so this is our tangent space. But just like in the Ricci soliton theorem, we're always on this direction, H. So where did K and H come from? They come from the Cartan decomposition of a Hermitian symmetric space. And so this is a natural inner product. So we're going to get a bijection between metrics. So if you give me a metric in this module, let's call this, say, GV. I can write down an inner product which is going to correspond to a metric on this homogeneous space by just taking a positive multiple of killing form in the H direction and adding on GV. Okay, so it turns out, I mean, this is because this is a classical fact that there's a unique G invariant metric up to scaling on this Hermitian symmetric space. So this is the only possibility for what the inner product can be here. So it turns out to be enough to characterize these. And what we end up having to compute is what's called the centralizer of the representation. And to jump ahead, we get this explicit parameterization. So I just wanted to show this to finish. So for example, what we see happening here is that this space is basically parameterized by components coming from the centralizer of the representation. And so in particular, for example, if we take this example, this is one of the representations of complex type, meaning the centralizer is a copy of C. And so that means you get a one-dimensional family of representations. In general, you can extend this and you can sort of take sums of these representations and still get irreducible metrics. And that's how we can if you take D copies of D sums of this representation, that's how you can get a C to the D moduli space. Okay. How do we show that these metrics correspond to different? So what we do is we explicitly compute the Ricci tensor, which was convenient because we had, that ties in with the Ricci soliton problem. And when we explicitly compute it, we show the spectrum of the Ricci operator is different. So that's how we can show that they're not isometric metrics and they're genuinely distinct. Okay, so that's, with 1 minute, that's exactly what I wanted to talk about today. There's a lot in the paper that I didn't get to, but yeah, I hope you learned something. And yeah, thank you for your attention.
Oops. Thank you for a really fascinating talk. Are there questions? I have a question. When you get this big moduli space of metrics, which sounds amazing to me that you have so many, are the isometry groups, can they be bigger than what you originally started with, or?
That's a good question. Yep, the isometry group is defined by you take this. So yeah, that's explicitly computed. The isometry group, you take this. It's built out of the centralizer, and then you intersect it with SOV. Yeah. So as you extend the metric, then this does get bigger. Yeah. Yeah. So they change. Yeah. That's right. Yeah. So yeah.
Oh, go ahead.
Yeah, no, it was definitely very surprising when we saw this behavior. But with that said, another thing that's very interesting for the future is where was this part? When you fix one, you also can we computed so the transvection Lie group always acts transitively. It's a classical fact. We computed what's called the no-meso group, which is the full isometry group. And that's why we had to develop this algorithm to compute the isometry group. And then you can see that there's a big gap between them. But then the problem is that the simple reason why we couldn't, so that means that at Lie algebra level, any Lie algebra that's sandwiched between those two, should correspond to a new transitive group action. But there's a slight technical issue, and actually this goes back to stuff at the start of the talk and to like the classical Cartan stuff. We lose control from like the algebraic level going back to the manifold level because when you don't have the exponential map isn't surjective is a simple reason. So when you have like so you don't know you can go back in general. And we know we can go back for the full isometry group because we prove it's the full isometry group. We prove you can always go back for the transaction group because that's how we proved our structure theorem. But for the guys that are sandwiched in the middle, I don't know what to do. So that would be nice. I mean, it would be pretty cool to get like lots of different, so many different metrics, but then you fix a metric and there's many different transitive group actions. Is very unusual behavior. And that's really kind of why we were so surprised by this, that it's very unusual that you get such a rich sort of thing going on and it's just homogeneous. Usually it's just homogeneous spaces, but you get this very surprising behavior to us.
Yeah, it's really striking.
Yeah.
Yeah. Are there other questions? Well, thank you very much.
Okay, thank you.